Good morning, everyone. Welcome to our webinar this morning. Our topic today is how to let SOLIDWORKS Simulation find the best design for you. I'm Joelle Guinette. I am the Territory Manager for Eastern Canada, so Ontario to the Maritimes, and I have with me Michel Cloutier, who's a Senior Solutions Consultant, and I will introduce him in just a few minutes. So in the last few years being with SOLIDWORKS, I have been traveling quite a bit. Usually 3 weeks out of 4. And apart from making calls or apart from getting emails on my phone, the application that probably gets used the most or was getting used the most before pandemic hit was navigation tools, right? So either Google Maps or Waze were getting used very often. And I compare these tools very much to simulation because at the end of the day, I'm looking to get from point A to point B, and I'm looking for these tools to get me the best path and direct me to the best solution. And that's often what simulation is used for, to guide your design to get to the right place. But on top of that, you can add to this, right? And you can optimize that path within these navigation tools that either I'm looking for the shortest time, I'm looking for the shortest distance, I'm looking to avoid tolls of any kind. So there's some constraints that you can put in these to optimize your path based on your desired goal. And this is what we're going to do today, is talk about these same types of requirements and tools within simulation. I truly believe that simulation is an essential part of design, but if you're going to do it smart and work with the tools as easily and as best as you can. And as the topic says, if you can let the tools find the best design for you, then you'll be ahead of the game. So before we get going with this, just for those of you who are new to GoToWebinar, little go around, there's a panel on the right-hand side of your screen. There should be an orange arrow that you can use to close that panel so that you can see the full screen. If you are using computer audio, which is probably the default, hopefully it's coming through properly. If not, you can always change to phone audio. By clicking on that option, it'll give you the phone number and accesses to get on that way. Just remember that there may be some long distance charges if you're doing that, so be wary of doing it that way. There's a section for handouts, so there's a few documents that are there that you can download at any time during the presentation. But the most important part of all this is the questions panel. If you have any questions that come up during the presentations, please don't hesitate and write them in there. May not want to hit send right away just in case we cover it, but write it in as you think about it. And if it's not covered, then please do hit enter so that we have your questions. There's a lot of material to cover. We may not have time to get to them, but we definitely know who's putting them in there, and we will get to you separately if we need to. So without further ado, I will introduce now Michel Cloutier. He's been with SOLIDWORKS for 15 years, and in 15 years has been a solutions consultant. So the intent is we talk to our customers, we find out what they're doing, what they're not doing, how they're doing, and propose solutions for them. And today, Michel is going to enlighten you on different ways of optimizing in different ways with different tools and different solutions from SOLIDWORKS. So Michel, I'll hand this over to you, and I'll come back at the end to close.
Awesome. Well, thank you, Joelle, and welcome everyone. Good morning. I hope no one is superstitious today. We are Friday the 13th, but with simulation tools, we'll get through this really nicely. So let's get to it. Let's get to our topic of the day. How to let SOLIDWORKS find the best design for you. Now, today I want to talk actually about a few different tools, not just one, not just two, actually a couple. I'm gonna start by covering design studies. I want to talk about design optimization, and I'll kind of clear the nuance between what I call design studies and design optimization. And then we're also going to talk about topology optimization, which is really new. It's been added in like 2 years now. Inside of Simulation Professional, really cool technology, I have to admit. And we'll even go into some more optimization with motion, with CFD or fluid dynamics. So we'll cover a broad range of tools today, and I hope you're gonna enjoy what we have for you. So The first thing I want to cover today is design studies. Now, design studies is not really an optimization tool in my view, but you can actually use it to get a good sense of what you want to optimize for and figure out a lot of things with it. Bonus point, design studies are actually in basic SOLIDWORKS. Now, if you use, in my case, I'm going to use design studies with simulation data. So obviously I would need simulation. You would need simulation to do that. But design study itself is in SOLIDWORKS core. So let's talk about design study and how I'm going to use design studies today. So I'm going to use design studies for two things. First, I have a scenario. I have an assembly. It's actually, I'm going to be working on a suspension, car suspension model. But I want to find two things. I want to find the worst load combination, because in often cases where you have any type of design, great if it's going to be loaded in one direction with the same identical load all the time. That's fine. That's great. But often cases you will have maybe a combination of loads, like a lateral with lateral and vertical loads with different values, um, different types of loads and force of loads. So I'm going to use design study to actually look at different load combination on an assembly, and then I'm going to use it again to find a acceptable geometry. And I didn't put optimized geometry, I said acceptable geometry, and I'm going to talk about the nuance of that. So first, let's look at how we use design studies to find a worse load combination in an assembly. And before we actually use design study, I just want to go through the setup of the simulation I used. So when I look at this assembly right now, you see I have this suspension model. And the first step in any simulation is to assign material. So here I'm using alloy steel that has a yield of 620 megapascal. And I use the same material throughout my assembly. Then I actually use some features inside of simulation called connectors that allow you to simplify the simulation model. So I don't need to model the spring, I just define it as a connector with a stiffness ratio. I did the same thing for the pin, so there would be pins in there. I didn't model them, so I'm simplifying my simulation study by creating virtual pins, if you'd like. Then with regards to my loads, I'm gonna set the bottom holes and top holes to be a fixed hinge. That means it can rotate but no translation. And then the last thing I need to do here is to assign the force. Now the force is going to be assigned on the hub. So I'm selecting that. You see the arrows pointing a little bit everywhere, but I'm using a plane to define the direction of that force, right? So I want the force to be vertical and normal to that plane. Instead of putting a value, I'm going to create parameters, and we'll get back to that in just a moment. So there's going to be two types of loads in this assembly, a vertical and a lateral. So I'm creating the first parameter, which is a vertical load of 225 newtons, and then a lateral parameter. And for the first study I'm going to do, I'm going to leave that at 0. So basically no lateral load, just vertical. But I'm still going to add a comment so I can find it easier. And now I'm going to assign the force normal to the plane to be, I'm going to change the direction, and then the force on the side, the lateral load, to 0. So that is 0, but I'm still assigning it. It's not going to take it into value when I'm going to run the simulation, but it's still set, and I'm going to repurpose that a little bit later on. I run the simulation. You see here, this is running real time, so it's fairly quick. It is a fairly simple assembly, but those connectors allow me to actually solve this faster as well. Now, the warning was about large displacement. I'll still be going to solve it without large displacement, but one of the things I always do when I run simulation, when I get results, I animate, just to make sure I've applied the loads in the right direction, that all my simulation setup is correct. And very quickly, I got my inputs, or my outputs, I should say, my results, where we can see the maximum stresses and the maximum displacement. Right now it's like 6.5 millimeters of displacement, just about. So now that I've created this simulation, what do I actually want to do with the design study? So here's how we're actually going to use the design study for. Right now, I just ran a static simulation problem. Now the design study, what I'm going to use it for is to test different load combination, right? So for example, a car suspension like this has different load combination depending what the car is doing. If it's just parked in the driveway, well, it's stationary, there's only a vertical load, there's no lateral load on the suspension. But while you drive it, depending on the type of road, smooth, bumpy, or in a curve, those loads are going to change, right? So what I've done is actually I have a little text file here that kind of shows the different load combinations. So if you look at the little file here, and I can actually help you do that by zooming in. There you go. So when we look at this, you see that in a stationary vehicle, the load is going to be 0 lateral. It's not moving. So, and vertical load is going to be 225. That's in newtons. And in a moving vehicle on a smooth road, the combination is going to be 60, 185. Moving on a bumpy road, 72, 385. And moving in a corner, 115 and 900 newtons. That's going to be my different load combinations. Now, I've actually already ran the first combination, right? 225 and 0, 225 vertical and 0 lateral. So without design studies, what I would do is actually, you could simply copy the studies, copy them 3 times over, go in, change the values for each of the 3 copies, and run all the 3 copies separately. Design studies actually allows you to do that much faster. So here's how we use design studies to actually speed this process up. So back inside of SOLIDWORKS, I'm creating a new design study. And now I'm going to set my variables. Now remember, the variables were the loads. So my first variable is the vertical load, and that's going to be discrete values because I got 4 scenarios, right? So that's my scenario. So I'm going to simply copy this from my text file, move that over, and come over here and paste it. And now I'm going to switch to a table value. So as I'm doing this, you see it's creating these 4 scenarios. Now I'm going to add my lateral load, and then I'm going to add the values for each of those combinations. So 60, 72, and 115. So that's my 4 scenarios I want to solve. And before I run my design study, I want to add some not really constraints, but I want to monitor the stress in my assembly and also the displacement. So I want to know for each of those values, what's the stress and what's the displacement. Once I've done this, I simply hit run. So you see, I didn't create 3 and 4 different copies. I just created one design study, set all my parameters in a table, and now SolidWorks is simply going through and running each of those 4 scenarios. Now this is going on real time, so it gives you an idea of how fast it is. So it might take a minute or 2 to solve. But it's already running scenario 4 right now, and you see actually as it's running, you can actually see the data being filled in the table as it's going along. So the last one here is going to run. We'll just let that go. And maybe after a minute and a half, I got all my results for all my different scenarios. And now I can actually go in and cycle through my different results. So here's my stress. And just by clicking on the scenario, I got the updated result plot on the top here that I can cycle through. Now, by looking at these results, we see very quickly that scenario 5 is going to be my worst case when we look at the stresses, but we could also go in and look at displacements. So that's another thing I wanted to actually look at. And right now the displacement is about 26 millimeters. So what does that mean after, right? So what have we done so far? So far we simply looked at different combination, and what I did, I ran this earlier, put that into a graph just so it's visual, and now we can see the 4 scenarios, right? My 4 load cases, I should call them, with the stresses and displacement, and it becomes really obvious now that it's the 4th scenario that is the worst load combination. So if I want to do any type of design optimization, or if I want to tweak my assembly, I should actually use the data from the 4th scenario, because that's the worst case, right? So we use design studies to find the worst load combination. Now we know that. Now I'm going to reuse again design studies, but this time around to find a acceptable geometry. And I don't say optimize, I'm going to say acceptable. And we'll talk about optimization right after this. So with that, what I do is that I know the worst case, right? We found that. But right now, on that worst case scenario or load combination, my current factor of safety is below 1, meaning that if I would take that, put it into a car, it would fail. That's sure of it. But I want to have at least a factor of safety of 2, right? So right now I'm currently right below 1. So you might be thinking, well, if we know where the worst the worst stress is, I'm simply going to double the thickness, and that's the end of it. But on a simple part, that might be true. On a complex part, that might be a bit difficult to find which value do you actually change to do that. So we're going to use design study to help us figure out the right thickness for that part. And also one of the limitations, I should say, or constraint, is that I don't want to have more displacement, more than 26 or maybe close to an inch of displacement to that, right? So I got 2 constraints. Basically, my factor of safety has to be 2 at least, displacement below 25, 26 millimeters. So let's go back into SOLIDWORKS and see how we would do that. So back inside of SOLIDWORKS Simulation, I'm going to create, again, a new design studies. But before I do that, actually, I'm going to go back in my original study and simply remove the link to the parameters, because I know this combination of load is the worst. That is not going to change anymore. So I'm simply going to change it so it stays the same for all my scenarios. Once I do that, I create a new design study. And my variables now are not going to be simulation data, they're going to be model dimension. And the first one is going to be the arm thickness. Now I could actually put many. I'm going to just go with the thickness of the arm right now. That's currently 3 millimeters. And that's going to be my variable. Like I said, I could put multiple variable, and we'll see an example of that later. But I want to test out different values between 1.5 to 8 millimeters with increment of half a millimeter. And also, as far as constraints, well, I want to monitor the stresses for the whole assembly. I want to monitor the displacement for the whole assembly as well. But more specifically, I want to make sure that my lower arm factor of safety is below 2. So I'm going to create a new sensor, pulling in some stress data, and I'm going to use megapascal. But rather than the whole problem, I'm simply going to say I want to look at the maximum for this selected entity, and the entity is simply the arm part. So now I'm kind of focusing more specifically on the arm, and I'm going to say, well, the stress in this arm has to be lower than 310 megapascal. Why 310? The yield is 620 for this material. If I want to have a factor of safety of 2, half of that. So that's 310. And the other thing is I want to have the maximum displacement, not of the whole system, but of the hub. That's where all the wheel is actually being fixed to. So that's my hub. I select the hub, and I'm going to say, well, I'm creating a sensor for this hub, and this has to be lower than 26 millimeters, another of my constraints. So once I've done this, I can see if I go to the table view, it's actually going to run 14 scenarios. Remember my increments of 0.5 millimeter, starting from 1.5 all the way through 8 millimeter thickness. So that's where the 14 scenarios come from. And I'm simply going to run. Now there's 2 methods here we can run. I'm going to use the fast method just because this is actually real time. Now, if I use the high quality, it's going to run all 14 scenarios. If I use the fast method, what it's doing is that it's going to run a sample of those scenarios. I think in this case, it might be running 3 or 4. I'm not sure entirely. It kind of depends on the total number of scenarios. But in the fast quality, it basically runs a sample and then extrapolates the data for the intermediate scenarios that has not been run. So it's really a quick way to just have like a quick view of where I should go, right? Where about in which area, in which scenario I'm going to be okay. So as this is running, like I said, this is running real time. Pretty much like the first design study we did, it ran, I think, 4 different scenarios. I think it's going to run 4 here as well. So it might take a minute or a minute and a half or maybe 2 minutes to run. But as it's running, notice the lower arm. You might see actually the thickness of that lower arm going from thin to thick to thicker. So that's what it's doing. It's actually going into the design dimension and changing those dimensions and running the scenario. Here you go. So that's my first scenario. And you see the red columns. The red columns obviously shows me that those are outside my constraints with regards to stress, right? So the stress is too high. So I know, from 1 to 7, I know that I'm over my stresses, but the columns in gray they haven't been ran. They're just there as extrapolated value. So if I want to have actually a real result, I can still go in and say, I think scenario 8 might be the right one. So I'm just going to run this one. I don't need to run every single scenario. I'm simply going to run this scenario that happens to be a thickness of 5 millimeters, if I remember correctly. So you see, it ran the scenario. My values are good. So I'm still under, I got my factor of safety that's below 2. Displacement is below 26 millimeters for scenario 8. I can even go in and look at the different results option, result plots. And now I found that all the different scenarios, this one is the one that makes more sense, right? So again, I've done what I've done earlier is that I ran all scenarios, and if we put them into a map, into a graph, I should say, and we look at the stress for the lower arm, right? Scenario 1 is very thin, right? So the stresses are high, and as my arm is getting thicker, the stresses go lower. There's actually a little blip in scenario 11. So actually, in this thickness, the stresses actually go up, which is kind of odd. So it kind of proves the point that making it thicker is not always better. But in this case, when we look at all the different scenarios, we saw that scenario 8 is the one that goes within my constraints of at least having a factor of safety of 2. So the stresses is 292 megapascals. So I want it to be under 310. So I'm good there, and the displacement is good as well. Now, why I was also monitoring the stress for the whole assembly is that you have to also keep in context of everything else. So yeah, I'm kind of looking at this lower arm bracket or part of my suspension, but when you look at the assembly, you realize that starting from scenario 5 about, the stresses in the rest of my assembly is not moving. So basically that's telling me as a designer, as an engineer, that when it comes around scenario 6, 5, or 6, the lower arm of my suspension isn't the critical component of my assembly anymore, because the stresses is now higher in another part of my assembly. So you have to keep in context of the assembly, and I think that's maybe one a key point of the message is, running simulation on single part is great, but always keep the context of the assembly, because in this case, we realize that even if I find the best design for my lower arm, another part will fail first. So the assembly itself is not any better. We have to look at the broad picture. But we still use design studies to get some results faster. So we use it for 2 things, right? So we found the worst load combination, and then we find the acceptable design. Acceptable, not optimized. Speaking of which, let's actually talk about optimization and how it differs from design studies. Now, optimization is really a simulation tool we'll find in Simulation Professional. And I'm going to actually work an example, a different example, still in car suspension. But with design optimization, the approach is different. In design studies, I tell it what to do, and it basically goes in and runs all those different scenarios. In design optimization, I tell the system what I want, and the system finds the best solution. So for example, so that's why it's called a goal-based approach. My approach is the goal. What's the end goal? Well, the end goal in this case is going to be to lower the weight, but I still have some constraints, right? So that's the part on the top right we're going to be using. So my goal is to minimize the weight or the mass of this part. If you're dealing in anything automotive, that's a very something that every automotive engineer do, but in many industries actually. Now, of course, I want to minimize the mass, but without any issues to safety, obviously, right? So what we're going to do here is actually run this, and before we, just to kind of look and see what we're going to do, those are going to be my parameters, right? What do I want to change to get to the goal of minimizing the mass? So I'm going to work off of 3 different model dimensions. Either they could be model, sketch, or feature dimensions, but the first one is going to be the thickness, and I want a range between 1/2 inch and 1.5 inches. The inside radius, that's going to be my range, and then the outside radius, that's also going to be my range. So 3 different dimensions on my model that I want to optimize so I can get to have the minimized weight. But again, with regards to safety, I want to keep a factor of safety of at least 1.5, and that for this material translates into 23,300 psi. That's going to be the maximum stress allowed if I want to have a factor of safety of 1.5, right? So let's actually see how we would do that. And let me just turn off the webcam for 1 sec and go inside of SOLIDWORKS and see how we would do this on the model. So here's my model. As you can see, my initial dimensions, 1.266, 3/4, 2 inch. And I ran the simulation just to show you how I set this up. First of all, cast alloy steel is my material. I used a fixed selection on top here, and then I put a force of 1,000 pound force. I run the simulation, I get results, I can animate the results. Like I said, that's the first thing I do is animate the result just to make sure my forces are applied in the right direction and my loads and everything is set properly. Now, I've just ran the simulation. I haven't done any design studies or optimization yet. So let's do it. I'm going to create a new design study, but within the design study, I'm going to make sure I check mark this option, optimization. That's really going to be the optimization tool, but the UI is the same. So once you get familiar with design studies, you're already familiar with optimization. Now, what are going to be my variables? Where I'm going to create 3 different variables, and those variables are going to be my model dimension. So here I'm going to simply call it thickness and select this dimension. That's my first variable. This is going to be inside radius. That's that. And outside radius. Here's my dimension. So I got my 3 parameters set. I'll say okay. Once I get those set here, and they now show up, and one of the main differences between design studies and optimization here is that I can have a range, but a free range, right? I don't need to specify a step. So if I remember correctly, my free range here, actually, so I'm going to transpose these values, right? So thickness, inside rad and outside rad. So those are going to be my range. So I'm gonna move this over here so I have it handy, but I'm gonna say, well, first of all, that's going to be, oops, let's 0.5, and this is going to be 1.5, right? The second variable is going to be my inside radius. That's also going to be a free range of 0.5 to 1.25. And my third variable is going to be the outside radius. Again, a range from 1.5 to 2.5. Whoops. 1.5 to 2.5, right? So I got now transposed all my values here. Those are my range, but remember I got my max stress to get me to a factor of safety of 1.5 needs to be 23,333. So that's going to come over here in my constraints. This has to be less than 23,333. There you go. And remember what? My goal, well, what's my goal? My goal is to minimize the mass, right? So now I've got this set up, and the last thing I need to do, well, is really just to hit run. Now, again, this is going to run different iterations, right? Now, the iterations, the number of iterations is going to depend on the number of values or the number of parameters I'm telling the system to change. And I'm not the one that decides which size or dimensions or thickness is being used in each of these iterations. It's the system that figures out what's the best value, right? So as it's going, you can actually see the data is getting back into that result view. You got some columns in red, so that highlights that these combination of sizes are not good because they likely, well, because they actually are above my maximum stress allowed. So fairly quickly, it just goes in and runs through all those different scenarios. And you see it's already completed. Now with this on the bottom here, I can, if I hit the initial, that's my initial thickness, right? And actually, like, we can pull in the stresses for that. So let's overlay the stress. So as it's going, it's creating all those different iterations. So that was the first iteration. That's my second iteration. That's my third iteration. You see this one here, the stress is really high. So that's not a good one. Here you see a lot of red, not a good one. So it went that and did that for what, 15 different iterations. And then it came up with the optimal design, with the optimal dimensions. So the system is actually finding, I'm not telling the system which dimensions to run, the system is actually coming up with the best answer. So that's really a big difference between design studies and optimization. Again, if we take all that data and put that back into a recap, initially with my set of dimensions I had when I started, I had a factor of safety of 2.7. Remember, my goal was 1.5. The weight of the part was close to 11 pounds. Now, again, my goal was to minimize the mass. So the optimized design now has a factor of safety of 1.6, which is slightly above my goal of 1.5, which is fine. But now the weight of that dropped to below 10 pounds. So I basically saved about 9.5% of weight saving on this part. I saved 1 pound off of a 10.5 pound part. So this is what optimization is. When you compare it to design studies, you don't tell it what to do, you tell it what you want it to do at the end, what's the goal, and then it figures out the rest. And just as a parenthesis, you might see a lot of similarities between design studies and optimization, and for a good cause, the UI is basically the same. But let's just take a scenario. For example, let's say I wanted to run design studies, not optimization, design studies on this part. First of all, I could not use a free range. In design studies, it's a range with a step increment. So let's say my step increment is 1/4 of an inch. If I would have done that with 3 different dimensions, that would have meant 100 different simulation scenarios. So simulation would have ran 100 different simulations just to get something that is okay, not optimized, but okay. With real optimization, because the system knows the end goal, I can give it a free range. It did the same, actually it did better with just 13 iterations rather than 100 scenarios. So a lot, it's less than 1/8, right? So it's a lot faster than than running design studies. So in cases where you have a lot of dimensions that you want to control and really optimize, optimization is really the way to do it. So we talked about design studies, and I made the parallel with optimization. And design optimization obviously finds the optimized design, not a good one, but not just a good one like design studies, but really the optimized one. Now, there's another type of optimization that actually was introduced just 2 years ago inside of Simulation Professional called topology optimization. And this is very different than the traditional design optimization we just saw. First of all, topology optimization is non-parametric. It doesn't care about any of the dimensions you have in your model. It just simply doesn't care. It just looks at the geometry. The idea with topology optimization is that you start with a maximum design space, like let's say a bounding box, and it's going to seek the optimal form based on the loads and boundary and loads I'm applying to the model. Let's actually see how it works. So back inside of SOLIDWORKS, I got this assembly, and you see the bracket here, like the lever, it's very blocky. Like it's modeled really quick. So first I create a simulation study, And the fixtures and external loads are going to be very similar, actually the same as if I would do any other type of simulation. So I got two bearing supports and I got a roller or slider face on the back end, so it can slide but cannot translate. It can just slide on a back face. And then my force is going to be 200 newtons on the top right cylindrical cut here. I use a plane to define the direction. Now that's where topology optimization starts working a little bit differently, is that we have a goal, just like optimization. Well, it is optimization, so it needs a goal. Now the goals are a little bit different. There's different types of goal, but one here I'm going to use is having the best stiffness to weight ratio. That's my end goal. And what do I want to do? Well, I want to reduce the mass by 40%. So it could be a like a absolute value or just a percentage. So my goal is try to reduce the mass but have a good stiffness to weight ratio. Now, because this is actually changing the geometry, the topology, I also have controls for regions I don't want to change. So these are important because there's points where I'm going to be fixing, putting a bolt, maybe a bearing inside. So these faces have to stay like they are. And again, because it's changing the geometry, I also have manufacturing control. So for example, I could take it to a 3D printer, great, but what if I still want to use a mold or create a part from a mold, for example? Once I run the simulation and I've defined all my controls and all my goals, I get a mass plot that shows me what and where I can remove material. So with this slider, I can simply go, if I want to make it lighter, heavier, if I pull it to heavier, I see the whole part. And the magenta, the dark color, is material that's not needed. And then if I pull it on the other end of the spectrum, I got a lot of material, and maybe I'm trying to remove a little bit too much material. But my default, where I was trying to remove 40%, gives me this output. Now that's great because that's a nice visual indication of where I can remove material, but I can also create a smooth mesh in the case where you simply want to take this result and send it to a 3D printer. So topology optimization is a great path to 3D printing. It's really awesome. So I can actually just save this into an STL file and basically print it. Now I could also just use this as a visual indication to help me redesign the part in a shape that's more that's better, but also using traditional modeling methods. So I can actually overlay that plot right inside of my assembly, and maybe I could simply come in and redesign or remove material from the original based on this plot. So this is also a great guide into helping understand how I should redesign if I want to redesign this part. And here's a redesign model, but redesign based on the topology optimization, but redesign as if I wanted to machine it on a CNC or any type of traditional subtractive manufacturing that we could run into, that we have, that is commonly available, right? So if we look, actually I have those little parts here. If you want to take a quick peek, let's look at them. So like I said, topology optimization is very different. So this was my original part, right? You see it's very blocky, just a basic shape of what I wanted. I ran the topology optimization. From the topology optimization, I saved this smooth mesh, and I have a little 3D printer. So you see, I took this part straight out of simulation of topology optimization, bang, on the printer, and here you see that's very complex shape. So obviously, to do something like this, you would likely want to do this on a 3D printer, but I could also use this as a guide to simply redesign this using traditional method, right? So the one on top here is the one I would redesign if I wanted to make it on a CNC, right? So if I move them around, if I actually overlay them, you'll notice the holes are exactly the same. Shape is different, right? But the holes and all the major mounting points are exactly the same. So topology optimization is great for that. That's something I have to say I'm really keen on. The topology optimization. So really the idea with topology optimization is to optimize the form. You give it goals and real life conditions. Remember, you can have simultaneous load cases if you want to. You can also include manufacturing process because the part can change quite drastically in topology optimization. Now, how do you want to make that? So you can use manufacturing controls to kind of restrict from doing something that you won't be able to manufacture after the fact. Now, like I said, this is a great path to additive manufacturing. Here's my example straight out of simulation. But like I said, it's also a great path to simply help you guide you into a redesign, knowing exactly where you need to focus your attention with regards to stress concentrations and areas and whatnot. So topology optimization is really good. Now, if we look at all three, right? So we talk about design study, optimization, topology, put them side by side. When we talk about design studies, we can do, with regards to variables, they can be discrete, so a set number, or you can give it a range with a step increment. There's no goals, you just tell it what to do, it does it, and there's no manufacturing constraints either. It's basically how you modeled it that is the manufacturing constraint. With optimization, the biggest difference or the major differences are a free range. So you can give it a range with your variable, but you say, here's my min, here's my max, whatever you find in between is fine by me. So it's a free range. But you can also give it goals, and any sensor can act as a goal. In my example, I had the weight. The weight was the goal, but it could be something else. Maybe the goal is to have a set factor of safety. Maybe the goal is to have a whatever, right? So you can use different goals, and to do that, you use sensors. Now with topology optimization, it's all about the shape. Really, variables are not needed. You don't need them. It just will figure out the shape you want. There is some goals, however, right? So depending on what you're trying to achieve, in this case, the example I was running, I wanted to have the best stiffness to weight ratio. There's a few other goals in there as well. You see them here. And also manufacturing constraints, because now we're really playing with the geometry. It's not mandatory, but you can put in some manufacturing constraints. For example, if you want to have something that you can mold or you can stamp, well, it's going to ask you for a direction of mold or stamp, and that helps you create something manufacturable other than 3D printing. So when we look at all those simulation tools, really optimization, leading edge technology to help you optimize the shape itself, not just the design variables, but really the shape. Now there's even a couple more simulation tools that you might not be aware of, and I'm gonna take maybe the last 5 minutes to run through them quickly. First of all, there's motion simulation, and there's also fluid simulation. So let's look at motion simulation. Here we got a medical chair, and that medical chair moves up and down. So there's an actuator that's pushing the chair up and down. And really what I want to do is to find the optimal geometry of that scissor assembly lift system to minimize the actuator required. So right now my actuator requires 2100 newtons to lift the chair with a patient on it. But I still have conditions, I have boundaries. It has to be higher and lower than the minimum maximum range of travel. So how do we do that in SOLIDWORKS Motion? So first of all, just to run through quick the motion simulation itself. So down here you can see the little actuator, and that's where I defined the motion. And basically the motion is between 0 and 2 seconds. It moves up. From 2 to 4 seconds, it moves down, gives me that curve of motion. And now I run the simulation and I get my linear displacement of the tabletop, I guess, or chair top, and also the maximum force required by the actuator to move up and down. And that gives me 2100 newtons. Now let's go into optimization, and my variables are going to be some of the dimensions of the assembly where you see the like the scissor length, the height, and also the piston position or the actuator position. My constraint is going to be the height, so it has to be not go lower than this amount, not go higher than that amount. My goal is to minimize the force required. I run those scenarios and I just, like I did before with optimization, I just let it go. This is also recorded in real time. So as you see, it's going through all my different scenarios, and motion studies are fast to begin with as well. So that runs pretty quick, and you already see some scenarios are red, meaning that maybe the force is more than it was initially, or maybe the height are outside of my boundaries. But you see here, it's running all those different scenarios up to the point where it's going to end up after 15 of them, I believe, 15 or 14. Yeah, 15 scenarios. After that, I can actually go in and look at all my different iterations. So that's my initial design. You see the geometry of the frame. That's iteration 1. That's iteration 2. I can cycle through each of those iterations to see the different geometry and dimensions that were tried, and that's the optimal. So that's going to be the optimal geometry required for this. So what happened? Well, when we look at the results, we started with an initial force of 2100 newtons. The optimized design now uses 14, for a little over 1400 newtons. So what does that mean? That means that by a simple motion optimization, I reduce the power requirement or the force requirement for that actuator by 1/3. That's fairly huge. I mean, concretely, that means I can either use a smaller actuator, right? Probably cheaper too, because it's less powerful, but also if it's electric, well, it's going to use or consume less energy as well to move the chair up and down. So that's pretty neat. We can also do optimization in flow simulation as well. So let's take a quick look at this. I got a little system with 3 different heat exchangers, and I want to have the optimal design by controlling the valve angle of each of those heat exchangers. I want to have really an equal flow rate in all of the 3 heat exchangers. So inside of SOLIDWORKS, how I would do that. So here's my little model. And as you can see, if I look into my mates, I have those valves controlled by 3 angle mates, right? So angle 1, angle 2, angle 3. Right now it's 30, 40, and 50 degrees because I didn't know any better. So I kind of went, like this and just threw in some values. My inlet is going to be 60 kilograms second. That's my flow mass in my inlet. Outside air pressure. My heat exchangers themselves, I simulated them by using a porous media. So I'm simulating there's some restriction here, like let's say a filter would be a good example. So with a porosity, and then I ran the simulation, and here's the result for this. Remember, right now the angles of the valve are 30, 40, and 50 respectively in degrees. And if I look at the flow trajectory, you can see that it looks like, some of the heat exchangers, there's more volume or more velocity going through some of them. It's not equal, and you can tell a little bit by the pressure as well, by the back pressure. Now in flow simulation, what we do is what we call the parametric study. So currently the valve are 30, 40, 50. I want them a range of value between 0 and 60. And then I basically let flow simulation create all of those experiments. The first one is 30 everywhere, but then it changes all the angles of those valves. And it's going to do this. In this case, it did it for 15 different experiments. And we can actually get the results, the cut plot results for all of those 15 experiments. And once it's done all those 15, I'm simply selecting and say, hey, which one is the optimal? And as you can see here, the valve angle, but the flow rate is equal through all 3 of them. So again, just a great way to figure out what is the best angle of those valves to have an equal flow rate throughout my system. You can see that the pressure is much more equalized right now. And when I look at the actual flow rate, now you can see that there's exactly an equal amount of flow going into each of those 3 heat exchangers. So again, if we put that together, we ran through all those different scenarios inside of flow simulation to figure out which one is the best one. And right now, the optimized valve angle is going to be 27 degrees for the first one, 3 degrees on the second one, which is almost fully open, and 32 degrees on the last one. And that ensures the optimal performance of my simulation model. So again, optimization doesn't stop at linear, static, or things like that. You can go into motion, flow as well. But I think that kind of wraps up pretty much what I wanted to discuss today. I'm already close to the hour, actually on the hour, so I'm gonna let Joël maybe close off. Right before I do that, just to a quick review
Go ahead,
which
that's
ones
important.
where, right? So like I said, design studies is in core SOLIDWORks. In my case, I use design studies in combination of simulation. So obviously you would need a simulation for that. But then topology optimization, well, optimization and topology optimization are in simulation professional, motion as well, and flow optimization is actually in core flow simulation. So that's it.
There you go. All right, great information. We are at the hour. It is lunchtime. I know you're all waiting to go eat. This is recorded, so if you want to access it, you can go to our go-to stage where all of our webinars are recorded. You can take a picture of this so you can access it later, or you will be sent a link by email in a day or so, or probably Monday, with the recording as well. So if you want to share this with anybody, please feel free to do so. If you would like to dive into any of these topics a little further, we'd love to. Your resellers would love to help you with that as well. So you've got lots of options to find out how you can either best use the tools that you already have or invest into new ones so that you're working more efficiently and you just have better products at the end of the day. So we thank you for joining us today. Again, Friday the 13th. Have a good one, and we'll see you on our next webinar. Have a good day, everyone. Bye for now.
Thank you. Bye.